Welcome viewers and subscribers. Welcome back to my channel and welcome back to another video. In today's video, I'm going to show you how to calculate the maximum deflection for a two-way slab. Now, this two-way slab consists of a dimension of 20 feet by 20 feet. A 20 feet by 20 feet slab is typically what you have for a double garage in your residential home. All right. So the reason why I'm doing this calculation or this demonstration is that oftentimes when you send your building plans to the municipality, once the slab exceeds 20 feet or more, then they usually request of you to put in a flat beam at the center to limit the deflection. So I am going to prove or going to disprove if that is necessary. So I'm going to utilize the formulas from my civil engineering manual as well as the ACI code. So I want you to watch the video, I want you to share the video, and I want you to like the video. And in the event that you have any question, shoot me a comment in the comment section. I'll be more than happy to answer your question. Stick and stay to the video. All right. So here we have it, viewers and subscribers. So the reinforced concrete slab is 20 feet in the X direction and 20 feet in the Y direction. And it has a thickness of 6 inches. Now, the first thing to do is to determine if your slab is a one-way or a two-way slab. So how to determine if this slab is indeed a two-way slab? It is the length divided by the breadth, and if that ratio is less than or equal to 2, then your slab is a one-way slab. So therefore we have 20 feet divided by 20 feet, that's equal to 1, and it is less than 2, so therefore it is a two-way slab. All right, so that's the first thing. Now we are going to take a 1 foot strip of this slab, a 1 foot strip at the center. Usually in engineering design, we do not design the entire length or the entire width. We only design for 1 foot, and we replicate that design for that 1 foot throughout the slab. All right, so we take a 1 foot strip, and if you note, we turn this 1 foot strip into a beam, right, into a simple supported beam. So we're going to design this 1 foot strip of slab as a beam. Okay, so the span, which is evidently going to be 20 feet, right? So here we have now, so we go to the ACI code. The first thing we determine is the amount of loads we're going to use in this slab. So ASCE 798 is where you obtain the values for the live load. So we're going to use a live load of 40 pounds per square feet, coming from the ASCE table. ASCE stands for American Society for Civil Engineers. All right. So the second thing, we go to the code, which is ACI 318-19. So this is the 2019 ACI code to determine how much is the maximum allowable deflection. So if we go to the code, and we should go to the table for that. So it is, let me see if I can find it very, very quick. So it is control find, which is 24.2.2. All right. So here we have it, folks. So in this instance, right, we come to the table here for maximum permissible calculated deflection. So we have here, we're going to use, since we are designing a floor slab, we're going to use floor, and it is the immediate deflection due to the live load, which is L over 360. So we're going to use L over 360 for our allowable deflection for this slab. All right. So we can go back to the calculation now. So this is where we get the L over 360 as per 318-19 table 2.24.22 for our ACI. All right. So the load, so we're going to convert that live load of 40 pounds per feet square to pounds per foot. We're going to convert this 40 pounds per square feet into a uniform distributed load. So how we can do that? We just simply multiply that 40 pounds per square feet by 1 foot, since we are only doing a 1 foot strip, and this works out to be 40 pounds per foot. All right, so that's the first step. The second step is to calculate the dead load of the 1 foot strip of the slab, right? So our dead load is going to be the 1 foot, right? The slab is going to be 6 inches thick, which is going to be 0.5 feet, and the length of the slab is going to be 20 feet times 150 pounds per cubic feet, right? So the weight of reinforced concrete is 150 pounds per cubic feet, or 24 kilonewtons per meter cube. All right, but we are using feet and inches in this instance, so we're not using kilonewtons per meter. All right, so to convert the unit, so when we times that 1 foot times 0.5 foot times 20 foot times 150 pounds per cubic feet, we are getting this 1 foot strip of slab to weigh 4,500 pounds. All right, but in order to calculate the weight per foot, we have to convert this 4,500 pounds into pounds per foot. So since the span of the slab is 20 feet, we divide that 4,500 pounds by 20 feet, and we ended up with 75 pounds per foot, right? So using LRFD design method, we're going to use, for our ultimate weight, we're going to use 1.2 times the dead load plus 1.6 times the live load. All right, so our ultimate weight is going to equal to 1.2 dead load, which we just work out to be the weight of the slab, which is 75 pounds per foot, plus 1.6 times 40 pounds per foot, which is the live load. So when we do that, we have 90 pounds per foot plus 64 pounds per foot, and the total of that is 154 pounds per foot. So we're going to use a weight in terms of live load and dead load on this beam to be 154 pounds per foot. Now our deflection, our maximum deflection, is going to equal to 5 times double L to the fourth over 384 EI, and that must be less than or equal to the length divided by 360 for this slab to be safe under code. So let me show you where I get this 5 double L to the fourth over 384 EI. So I go to my civil engineering manual, right? And we look, so the slab or the beam is going to have this description. It's a uniform distributed load over it, and our shear force will look something like this, and our bending moments is going to look something like this. So therefore our maximum deflection is going to equal to 5 double L to the fourth divided by 384 EI. That's where I get this formula from. All right. Now, having established that, we're going to find out each of these components. You know, we calculate the weight already. We know the length. We have 384. So we determine now to find out what the elastic modulus of concrete is going to be, and I, which is the moment of inertia. So for normal weight concrete, we use the elastic modulus of concrete shall be permitted to be 57,000 the root of FC prime. So FC prime is the stress of concrete that we're going to use for this calculation. So let me show you where I get this formula from. It is taken from the ACI 31819 section 19.2.2.1. So if you notice by code, it says for normal weight concrete, the EFC shall be equal to 57,000 the root of FC prime, and the unit is in pounds per square inch. So this is where I obtained this formula from. Okay, so let's get back to the calculation. Right, so when I work out the elastic modulus of concrete, that is 57,000 the root of 3,000 psi. That works out to be 3,122,019 pounds per square inch, or 3 times 10 to the 6 pounds per square inch, right? So we can say that the EFC for a 3,000 psi concrete is 3 times 10 to the 6 psi. Our moment of inertia now, which is BD cube over 12. So what we do now is I assume a 1 foot length of the slab, so, and then cut a section through that 1 foot length. So the 1 foot length is going to be equal to a thickness of 6 inches by 12 inches. So since we are working out our moments of inertia I, those values has to be in inches. So it's going to be 12 inches times 6 inches cubed divided by 12 inches, and that works out to be 216 inch to the fourth. All right, so now we can plug in our formula. So we have our W ultimate weight, which is 154 pounds per foot. We have the length of the 1 foot strip of slab to be 20 feet. We have our EFCs, elastic modulus of concrete, to be 3 times 10 to the 6 psi, and we have our I, moment of inertia, which is 216 inch to the fourth. So we're going to plug this into the formula now, which is 5LL to the fourth over 384 EI. So when we plug that into the formula now, all these values into the formula, I am getting a result of 0.17 inch. Okay, so the maximum deflection of this 20 feet by 20 feet slab is going to work out to 0.17 inches. All right, so now our L over 360, right, over L over 360 is going to work out to be 0.67 inch. So the allowable, the permissible allowable deflection for this slab is going to be 240 divided by 360 is going to be 20 times 12. So we bring that 20 feet to inches, which is going to be 20 times 12, 240 inches divided by 360, which works out to be 0.67 inches. So the allowable deflection for this slab is going to be 0.67 inches. So therefore, our maximum deflection is going to be 0.17 inch, and our allowable deflection is going to be 0.67 inch. Therefore, the deflection in this slab is okay, because the calculated maximum deflection is less than the allowable deflection. So that simple tells us that this 20 feet by 20 feet slab does not need a flat beam at the center to limit the deflection. All right, because we have just proven you by the code, right, and do the calculation methodically, and it does not shows that the allowable deflection is more than the calculated maximum deflection. In the event that the maximum deflection was more than the allowable deflection, then we could put a sleeper slab. And again, from my perspective, a sleeper beam or a flat beam is a stiffener. Okay, it is not a load carrying member per se. When you put in a flat beam at the center at midspan, you're only stiffening the slab at midspan to limit the deflection. In my opinion, the correct thing to do is to calculate the load that is going towards the center and design the beam to carry that load. And that beam has to be a down stand beam, not a flat beam. But what I would say, for a 20 feet by 20 feet slab, even though the calculation is not showing that a flat beam is necessary, I will still put the flat beam at midspan to stiffen that area. And the reason why I'm doing that is out of an abundance of caution that we in Jamaica, we are in a earthquake zone. And if we get a violent earthquake of a certain magnitude, you want the slab to be stiffened so that it doesn't subject to damage. Okay, even though it is not showing that it is going to need a flat beam at the center, I will still put a flat beam there. Okay, and the municipality, once they see 20 feet, they're going to say, you have to put a flat beam in it. But I just showing you the calculation that 100% it is not necessary based on code. But I said I will still put it, right? So I'm not saying don't put it, right? And it's up to your engineer. Every engineer doesn't think the same way and doesn't process things the same way, all right? So what I do, I even increase the length of the slab to 25 feet and see what that deflection is like. All right, so the allowable deflection for 25 feet is going to be 0.83 inches, right? And when I run back that 25 feet into the formula, the maximum deflection is 0.42 inches. So you see, again, it is still safe up to 25 feet because 0.42 inches is less than 0.83 inches. But out of an abundance of caution, I would still put a flat beam in the slab just to be sure, right? And this is for a residential building, not a commercial building. If it's going to be a commercial or an industrial building where the loads are much greater, you will have to do the calculation, and I'm sure it at that instant is going to need a flat beam or a downstand beam, a design beam to withstand the load. For a residential beam, for a residential home, which is going to subject to a load of 40 pounds per square feet or 50 pounds per square feet, then you would, when you work that deflection out, after in time you're going to work out, to get good numbers, and that slab is going to be safe. But I said, still put the sleeper slab. All right, so I have come to the end of this video. So join me next week. I'm going to do the calculation for a one-way slab and show you what the deflection is going to be. All right, and I think the video after that, I'm going to show you now that in the event that you want a beam to withstand the deflection at midspan, I'm going to show you how to calculate the loads that is going towards that beam and probably calculate the amount of reinforcement that that beam is going to need to withstand the load. All right, so that is it for this video. Ensure to watch the video until the end, and these videos is just to enlighten people who want to learn. And when I do this calculation, I learn myself, I reinforce what I've known already, right? And it does serve to keep me going. All right, so watch the video until the end. Take care until I catch you again. Enough respect. All right, good.